Welcome. As is the name of the podcast, we start with thinking about a problem or opportunity, which is the first episode for any topic that we discuss in this podcast. Then we build the product in the second episode, and on the third episode, we talk about how to scale a company using that product. We repeat the sequence of the nature of episodes for all the topics that will be talked in this podcast. So, yes, one topic, 3 episodes. That forces us to think, build, and scale. Towards the end of all 3 of the episodes, you will receive a full-fledged business plan and product development architectural plan to be used for your startup or your organization. Of course, you will have questions and you might need a person to build it all together. If so, please contact me at pretoria.b@outlook.com for discussing a tenure as a remote or on-site fractional CTO for your company. You're also welcome to go through the introductory video of this podcast if you haven't already had. In the previous episode, we talked about how various different companies are at different stages of their existence, and then they could develop such an equipment. But also we talked about some brief discussions on the type of market and customers. I touched the concept of using a V model for your product generation process, and today we will talk more concrete engineering topics on the development of Transmission Electron Microscope. We have been calling this product TEM Gen Z, Transmission Electron Microscope Gen Z, just because it's futuristic. Before going forward, I would like to bring to your attention that no company secrets or confidentiality agreements have been or will be violated consciously while recording the episodes of this podcast. Everything presented here is an amalgamation of knowledge and experiences from various industries and trainings that I have had. The information presented here, to the best of my knowledge, does not overlap with any confidential trade secrets or of any of the companies that I have a non-disclosure agreements with in the last 2 decades. Let's go to the second slide. Look what we have here, our V model embedded with Design for Six Sigma statistical tools. I talked about the importance of V model incorporating Design for Six Sigma tools in the introductory video. I also mentioned that I will make a series of episodes where the Six Sigma tools are described in detail. And I also, in my previous episode of this topic for TEM Gen Z, I also described why a V model is necessary for your organization. Long story short, the reason why I'm talking about a V model, which is a product generation process, is because as a company, as a board of directors of a startup or scale up, you will need to show that you will need to show your shareholders and your stakeholders that you can actually run the company. And how would you show them? You need to show them through these organizational structures. You need to show that, yeah, you have people in places at various different levels, and each of these levels are communicating with each other through I don't know, more than just meetings. They are communicating through each other through a series of documents or a series of processes. All right, let's go a little bit deeper today. Today is all about the details. So I'm going to go very, very technical, but at the same time, I could go even further into the details, and I'm not going that further into the details because I want to give my audience a full-fledged view of how to make a business around a capital equipment like Transmission Electron Microscope. Remember that. That's the perception of my episode. So let's say you are one of the board of directors of a startup or a scale-up, and you want to make a capital equipment like a Transmission Electron Microscope, or a hydrogen-fueled car. That's actually going to be the topic for my next episode, next topic, by the way, of this podcast. Or you might want to build a lithography equipment. You might also want to build or you might want to build a medical device, right? My series and my podcast is about giving you the tools and the information that you need to keep in mind in order to keep your organization running. So I'm always talking from the perspective of uh, uh, the board of members, what you need to know and what kind of people do you need to hire, and how to make sure that these people give you the necessary insights to continue running your company further on and further on. So I will go into the details, but not too much into the exact details. Like I said, I could go even further on, but for now, I will stick to a higher level of talking. Schematics to realized products. Now look at this. This was one of the diagrams I showed in the last episode, but also during your pre-university or your university study programs, you might have seen such schematics that shows what a normal optical microscope does, what a scanning transmission electron microscope does, and what a transmission electron microscope does. You have seen this image, I'm sure, multiple times. How do you get from here, from the schematics, to the realized product? Well, we will look at the various components and various systems. It's not only the product that we will discuss. We will go into realizing the product. So think of this machine as a human body. Just like the human body has multiple systems, such as the skeletal system, the optical system, nervous system, cardiovascular system, respiratory system, digestive system. This machine also has various subsystems within it working simultaneously while talking to each other together to form the complete system that users can utilize and analyze. It's beyond incredible, isn't it? In due time, I will break down more such complex machines and show you how companies profit from the development of such engineering marvels, and how to target the product to the right market, and how to continue to leverage one's position in the market. With regards to the market type discussions, that'll happen in episode 3. Not everything is going to be done in one episode. That's why think, build, scale, but of course, before you reach a finished commercial product like that, you will have to go through the loops of requirements, and the very first requirement will be a functional breakdown like this. We have discussed this slide previously and very properly in the first episode itself, so I won't go into the details of it now. You want to know more about it, please go to the first episode of this topic and check it out. Let's go to the main page. Now let's go back to the V model, shall we? Here we go. This is a very messy and difficult part. I'm talking about the fact that this is where corporate and especially engineering companies become quite messy, because information about something that is done here will be available here. Information that is done here will actually be confirmed here. So you see, it's a bit of a mess, because a lot of it is hindsight and a lot of it is foresight, and a lot of it is just communication. So it's a very difficult part. And I wouldn't say that sitting in the board is not difficult. That is also an extremely tiring and energy consuming work, because you really have to find the right people. These people that I'm writing here, marketing, system engineering, integration, research, PMO, all of these that I'm writing here, you need to find the right people to be placed as department heads or as sector heads, so that they know what they are doing and they can provide you the final product that you can make money out of, your beautiful, glorious TEM Gen Z. It is an actual picture of an actual transmission electron microscope developed by Thermo Fisher. There you go. All right. Engineers and project leads quit or get promoted mid-project. Managers vanish or micromanage. Suppliers go back on their word. Software does not understand mechanical and vice versa. Electronics and software are supposed to be brothers in arms, but they generally don't even understand each other or even talk to each other, etc., etc., etc. That's why I call it the messy part. But remember, I mentioned in my first video, if you are a visual thinker, please watch the next episode. And I meant this episode, where I go deeper into each of these slides along with images and pictures to explain my point. In this episode, it is good to use two of your sensory organs, your eyes and your ears. It's better to receive the full experience, but listening alone also works. It's a podcast after all. Development of a transmission electron microscope involves specific steps, considerations, and stakeholders. The first part of any development process is system level thinking and setting the requirements. As you see here, objectives of this phase include establishment of the foundational requirements and specifications of the TEM. We discussed this in the V model as well in last episode. I'm not going to go too much into it, but basically the system architecture and performance criteria are set to ensure that the TEM meets the expected standards of precision and functionality in that particular market. Market selection is also very, very essential, and I'll talk about it properly in the third episode. Previous episode, we touched upon certain activities like market analysis and customer requirement gathering and system specification development, etc. Basically, all of those things should be done at this stage where you understand the current market trends, what the competitor is offering, and then the potential technological advancement that the market is ready for. The market also has to be ready for it. AI is taking a while to speed up and to take over the market. They have been talking about it since a long time, but it took a while to get there, not because the technology was not great enough either, but the market itself, people were not open towards it. And now gradually with the advent of social media, the people are warming up to the idea of using AI in their regular work. And of course, GPT and others are still banned by various countries and corporates. Anyway, so the market has to be ready, the trends have to be ready, and then you need to check what the competitors are offering now and what more can you offer. Customer requirements gathering is where you gather the insights from your customers, as we talked previously, and you define your system specifications. The primary stakeholders, the primary people that are involved here are marketing, system engineers, or system architects, system integrators, the research, people who are doing the research on the scientific and usability standards, etc. And of course, your project management office, because somebody has to oversee the project timeline, budget, and resource allocation. If you go to the slide here, you will on the left, you will see a list which can be created to visualize and brought everybody on the same page. This list contains different components. Remember, I talked about a strategic bill of materials in my previous episode. This is what I'm talking about, a strategic high-level bill of materials. It tells you what different components are there in your system. So if for a TEM system, you have the electron source system, vacuum system. When I talk about system, it's exactly what I mentioned before, that just like a human body has a cardiovascular system or a respiratory system, the TEM has an electron source system. So just like your cardiovascular system is not just your heart, but your heart and your arteries and your veins and the blood around it, and your aorta and several other organs around it, your electron source system is a culmination of various different components. So you have the electron source system, you have the vacuum system, autoloader system, electron optics system, the cryogenic stage system, image detectors, supporting electronics, energy filter system, stage and mechanical driving system, the temperature management system, advanced monitoring and feedback system, enclosure systems, power supply, control, safety, hardware and fastener, etc., etc. In a bigger organization, each of these should go towards a particular department. In smaller organizations, of course, things are a little bit different and hectic. Look at this. To provide further elaboration on the design process, it's crucial to understand how each step is inherently linked to the next. Look here. The step one, which is your specifications and boundaries, are linked directly to the concept generation. The initial step lays the foundation of all subsequent design work by defining the operational parameters and constraints of the optical system. Any engineer always works with a set of constraints and limitations. For an optomechanical system, you have the optical performance specification, you have the mechanical constraints, the thermal constraints, environmental constraints. Environmental constraints could be humidity, vibration, and operational conditions. And then the overview of feasible tolerances and cost. When you go from specifications to product generation, the optical performance specifications directly inform the generation of design concepts as these specifications outline the goals that each concept must achieve. For example, why TEM and why not STEM? In 1930s or 1920s, when somebody from Siemens was working on the concept, all they got was a list of specifications. They got a list of things, a list of ideas that, we need so and so we need the concept of so and so. And then the first concept or the first image that was built for a TEM system was probably modified from the existing systems. That was a major breakthrough. That's how concepts come into place. They look at various restrictions and then you develop a plan for it. That's engineering concepts in general. From concept generation, you go to, of course, a concept evaluation. And of course, if you have multiple concepts to evaluate, you figure out which one is the best one to actually make use of. You can perhaps tighten tolerances and make plans on designing certain things. And you can already, as a people manager, you can already figure out what kind of talent and skills you will require to enrich the team with so that they can finally build the detailed design. It's a lot to worry about. In detailed design, you also get sensitivity table where you look at how each and every components are affected by the slightest disturbances. And of course, you have a budget error table where how much error in your production or error in measurement can you accept, because we work with errors. When you talk about Six Sigma or you talk in general high-tech equipment, it's all about looking at the errors. You can never say that 10 centimeter is indeed only 10 centimeter. It will be 10 plus minus 2, 10 plus minus 0.1. So that 0.1 or 0.01, that's what you as an engineer need to make. It shouldn't be a guess, but you need to make a judgment. How do you make a judgment? Through various concept evaluation, through generation of proper concepts, through looking at your specifications and your boundary conditions. Like I said, there's a lot of hindsight and a lot of foresight in engineering, especially in the world of high-tech capital equipment. All right, this design process is inherently iterative. It often requires multiple cycles through various different steps to address any issues discovered during detailed design or testing. This iterative approach ensures that the final product is not only theoretically sound, but also practically viable and reliable in its intended application environment. Each stage plays a crucial role in ensuring the final system meets the required performance and reliability standards. Let's explore each component of the workflow. The workflow is generally cyclic. You could see it in your screen if you're actually watching. They often require iterations between various stages, and each step is interconnected, and they emphasize a holistic approach to the design and development of sophisticated optical systems, ensuring that the final product is both feasible and functionally robust. This slide is an important one. At the very beginning of the concept of development of that architecture and development plan, you need various different standards to be maintained for your commercial equipment. These particular ISO standards are specific to TEM applications. So even though they're not directly medical devices, they still have to go through ISO 13485 because TEM is most of the time used in research laboratories that are a part of the medical equipment environment. You have to look at the ROHS, restriction of hazardous substances. You have to look at the electrical waste standards. You have to look at good manufacturing practices. On top of all of that, the documentation and record keeping in your organization has to be quite perfect. Hygiene and safety and your training and certification of your staff has to be to meet certain quality standards. This is why am I telling this? Because as a board of director, you need to know what kind of standards you need to place in for your company. Even if it's an app that your company is making, I'm sure there are standards that you have to take care of, and you have to be transparent about whether or not you're adhering to them to your stakeholders, to your shareholders, and your investors. We can talk about this later. Let's go back. All right. You might be thinking, why am I going so much into every details? This is the second episode, and this is the beauty of this podcast, that each topic will show you how various different aspects are required to make a commercially viable product. Whether a product is partly hardware or entirely server based, you will always need system design. You will always need to break a larger system into subsystems and subsystems and components. You will need to make codes or design CAD models for each of these components separately. You will need to beg and borrow previously existing standard components from suppliers and within your organization in order to save time and ensure commonality. Life becomes easier if engineers understand what executives go through and executives understand what engineers go through. Executives, after all, are responsible for providing the right tools and resources to the people who are working on tightly scheduled deliverables. And that is also one of the goals of my podcast, to bring different worlds within an engineering environment together. I'm appealing and talking to startup CTOs and CEOs, but I'm also talking to or established organizations, and I'm trying to show the level of complexity that is there or that should be there in your organization, the level of responsibility that you hold when you are actually developing and selling a commercially viable equipment. It is definitely not a joke, and it's an amazing ride, I must say. Translation to the second column of this presentation: mechanical module and component level. Objective of this phase is to develop constraints and set parameters for individual components and modules that make up the TAM. It ensures alignment with system level requirements. Here is where you start using CAD tools. As a mechanical engineer, or an electrical engineer, you start using CAD tools to create detailed drawings and specifications for each component. You have to identify and qualify suppliers who can provide the necessary components at the required specifications. Some of these components could be just vendor components that you're just buying off the shelf, and some of, like, your screws, your bolts, your fluid pipes, these are your vendor components. Your O-rings, you just get it off the shelf from thousands of suppliers out there. And then some of the designs that you're making, for example, I would show you. Let's go with this design that you just made in your CAD software. You actually have to make sure that a supplier is able to produce it, supplier is able to deliver it. And this is what you need to discuss with the supplier at an early level. Many organizations have a specific person dedicated to talk to the supplier, to different suppliers, and their only job is to actually talk to the suppliers, because they create a relationship. I really have respect for those positions, because they really are a bridge between 2 or 3 different companies, and they are emotionally mature enough to handle various different corporate cultures at the same time. Enough on that. Let's get back to our column 2. Here, the primary stakeholders are system engineering, PMO, mechanical, and other disciplines like electronics, software, fluids, maybe lasers, and then suppliers and sourcing. So our stakeholders changed from the first column to the second column. The first column had marketing, which is not there in the second column, because now it's not about the vision and the business goals. Now it's really about developing it. It's not about integrating. It's about really knowing what to do, what to make, and who to contact. All right. Design for Six Sigma tools that you use are a design of experiments and design FMEA. But We have talked about that in previous episode as well. Let's go to this slide, which is cascading the mechanical requirements from system and subsystem level requirements. The mechanical architect, this is where the role of a mechanical architect becomes so influential and so beautiful in the overall development of complex capital equipment. I love it so much. Role of a mechanical architect in influencing system engineering to establish mechanical requirements is quite an influential one. How does he or she do that? It's done by cascading your mechanical requirements from system and subsystem level requirements. This is so beautiful, right? Like in system and subsystem level, it's a bunch of words, it's a bunch of vision, it's a lot of requirements and a lot of dreams and hopes. But as a mechanical architect, you're often shattering a lot of people's hopes and dreams. You're often just telling them, no, we cannot do so and so, we can only do so and so. And that comes with experience and that comes with the type of industry that you're working on. But look at the slide. I really encourage everyone to, if you're listening to this in your car, thank you for listening, but please go home and I would say try again, try watching this episode, because I have provided quite a bit of information that you can actually take into your everyday work and you can learn from it, All right, so on the left, we have a hierarchy of components within a typical transmission electron microscope. And on the right, you will see various dependencies on the development of these components. Be aware that in a larger organization, the responsibilities of these dependencies are spread around various departments. You have the environmental and operational conditions, you have your mechanical interfaces, and you have electrical safety, tooling, etc. So in environmental and operational conditions, you have to take care of the medium, which is the substance or environment surrounding the system, that is air, vacuum, inert gas. So you remember I talked about in our introductory video, we talked about a sample grid, and then the sample grid takes the sample and places it into a vacuum chamber. Why does it place into a vacuum chamber and why is it not air? We also discussed that, and that is because we want the electrons to not interfere with the air. Where are these electrons coming from? That's from a different system. Amazing, right? So you need to, at every stage, at every different module or component that you're making, you need to know which medium are you working with? Are you working with air, vacuum, or inert gas, maybe? Temperature, you need to understand the operating and non-operating temperature ranges. They're actually critical for designing systems that must function under extreme temperatures or maintain stability across a broad temperature spectrum. Thermal interactions, that involves heat transfer issues between system components and the environment, and this includes consideration for cooling mechanisms or insulation. And then it goes towards, of course, design, but this is so beautiful. I love it so much. The system's pressure, the system's ability to operate under different atmospheric or vacuum pressures, humidity, the effects of moisture on your system components, including corrosion or condensation prevention strategies, requirements for particle-free environments, especially in systems like TEMS, where microscopic contaminants can affect performance. Fun fact, when I was working for development of EXE 5000, which was one of the greatest achievements of my life, our machine environments were 2,000 times cleaner than your operating rooms for surgery in hospitals. That's how clean we had to make sure that our components and our machines are. And it's not a joke, because these machines, they travel from continent to continent, go through checks, etc. How do you keep it clean? It's all design, baby. It's all enclosures. It's all a gigantic maze, and I live and breathe this world of complexity. And oh my goodness, I can go on and on. Like, look, if you're a podcast listener, you are not seeing my face right now, but I'm just gleaming. I'm just gleaming with the idea of so much of complexity, because I know the tricks and I know how to ensure that level of cleanliness, or how to ensure the level of prevention of humidity or prevention of thermal interaction, etc. It's just so wonderful to be a part of complex high-tech machineries. But anyway, the operating conditions, as you could see here, the general conditions that describe the operational limits and expected performance standards during usage, those are called the operating conditions. You have your thermal time constant or a warm-up time, the time that it takes for system to reach a thermal equilibrium. This is also crucial for precision instruments because they require stability before operation can commence. Because I'll talk about it later, but different materials have different CTEs, coefficient of thermal expansions. And if they are expanding, if they are not in a thermal equilibrium, then these materials, they expand, and that causes issues with accuracy and precision. But we will deal with that later on. Conditions inside every module, they have to be enclosed, and they definitely differ. The conditions inside the module differ from external conditions. Now look at dynamics. This is one of my favorite topics. Like, you have to make sure that the system is protected from shocks and vibrations from the environment, the natural frequencies, which is the eigenfrequencies at which the system components vibrate. They need to be managed to avoid resonance with external or operational frequencies. The damping coefficient, which is the effectiveness of the system in dissipating energy from vibrations or oscillations, they also have to be at a particular level, and that's where mechanical engineering becomes absolutely lovely. Lovely, I tell you. You have your optical elements, your light beam, optical components, coatings, materials, so on and so on. But you also have your mechanical the connections between different mechanical components, how robust and precise they should be. And then you have the mounting interfaces on different modules. So remember, like equipment, you have large systems. Think of it as the overall human body. And then smaller components, when they are developed, they have to talk to each other, they have to be connected to each other, and these connections are also very important to be taken into account. Generally, mechanical engineers from various different groups, they talk to each other in the language of tolerances. The tolerances could be in millimeters, could be in microns even, and the other engineer making the other module has to follow the space available from the previous module. So it's always a discussion, always a fight, in fact. And at the end, the system has to be built. That's the most important thing. We have to also look at various different mechanical layout, like the available volume, the mass, the center of gravity, inertia, your different supplies. TEM systems they produce a lot of heat, so you have to cool them. Therefore, water and gas interfaces come into place. Then you have to diagnose different problems with it. All of these, in fact, will influence the final parameter measurement and the information output and the various results. Therefore, they all have to work in tight specifications and tight tolerances. You have your electrical modules here where, you have to think about the heat dissipation, you have the interfaces, the grounding components, you have fibers and cameras and sensors, Lord, you have, of course, for safety requirements, you have various design rules that you have to follow for safety. And tooling, whenever you're adding a new component into the system, you have to make sure that they are tested first. So tooling could be testing those components, but tooling could also mean that when you're assembling the machine, sometimes you will need to develop additional tooling to assemble the machine. And I have, like I mentioned, I've worked in EXE 5000, and I have seen the level of complexity needed to develop those machines. They go as big as 1,100 cubic meters. So obviously your standard wrenches and screwdrivers will work, yeah, but you also need different other customized toolings to actually assemble them. That said, let's go back to our third column where our stakeholders are your team members. It's no longer only the mechanical architect, it's the mechanical engineers, suppliers, the system engineering, system integrators, and the PMO office. The PMO is needed everywhere because you have to keep the project in place. Manufacturing, fabricating, and assembling the TEM according to the finalized design is a real task on its own, yes. And then you also have to conduct assembly testing because you have to conduct tests to ensure that all mechanical and electronic components are functioning as intended. We discussed these things in the V model in the previous episode. And of course, you have to verify the system itself with comprehensive testing to validate the entire system against all the specifications. Let's go to this slide. The mechanical requirements and constraints to parts and assembly. Oh my goodness, this is such an amazing thing. This is an example project plan for the team. This is what a mechanical architect will provide to his or her team members, and based on their expertise and their ambitions and their interests, the team will probably receive some of the topics to work on and, of course, deliver at the right time. What a wonderful thing, isn't it? If you look at it from a higher level perspective, I think it's not a joke that what engineers are doing for corporate. We don't get enough credit for our determination and our foresightedness and also our hindsight insights. We don't get enough credit, but wow, engineers, we're humble people, but we don't always deserve or need to be humble. I would say, like, it's absolutely fabulous what we have been doing, especially capital equipment. Man, I mean, capital equipment, I can give you an example, could also be your satellites. That's a high-tech capital equipment. I'm going to do one of the episodes on that. It could also be, say, smart houses. Could be soon they're going to be high-tech capital equipment because it's just a machine, basically, your smart houses. Anyway, that's me going philosophical again. All right, look at this example project plan that the mechanical architect has created for the mechanical team. Now remember, the electrical architect has to create his own plan, the software architect has to create his or her own plan, the fluids architect, the optics architect, they all have to create their own plans. Why? When does this project plan come into place? Let's zoom out, shall we? Here. This is where the project plan comes into place. Like I said, you need 2 sensory organs for this episode. Okay, imagine the V model. At the bottom of the V is where you have your module and component level ideation execution. You have your suppliers, your toolings and logistics, and then you have the module and component level verification. This is where the discipline architects like mechanical architect, electrical architect, software architect, fluids architect, transportation architect, etc., etc., etc. These architects, they will make project plans for their team. I'm only going to show you the mechanical architect because I am not proficient in other disciplines. But okay, let's zoom in. Beautiful, right? I love it. I love it so much. Define and identify. We start with documenting specific design specifications, and it generally comes from a system. Then we make mechanical design specifications, work on block models previously. Prior to making detailed design, you always work on block models and create sensitivity analysis and risk analysis, get some feedback and figure out, you provide feedback or you receive feedback, but you generally give feedback to systems and PMO office to tell and identify your scope. So not everything can and should be done by the mechanical team. Certain things have to be done by some other disciplines, and that's where you identify your scope. Why is scope identification important? Because you already have a lot to do. Look how many things you need to do. You can't just do every single thing, right? So the scope identification is very important. And it's very important to communicate and be strong about it and explain it. Priority setting, like figure out which one has priority. Everything should go one step at the same time, but when you're making all of these project plans, certain things are at a higher prio than the others. Anyway, you also need to provide insights on the resources that you will need for future steps, your tooling development. Why is tooling needed? We talked about this. Tooling could be needed. Give me a second. Yeah. Tooling could be needed to assemble and integrate your components together, or tooling could be needed to even test out your component. So a lot of the tools that you see that are available off the shelf in the market might not, generally they are not suitable for your testing parameters and your testing needs. You have to make sure that the factory is ready to go when they receive the final product, so you need to give them the right documents. Additional experts, if they are needed, if you need a polymer expert or an optical expert or a marketing expert, I don't know, you have to identify it and you have to provide the insights to system level stakeholders. Then you would have to make sure that the suppliers are also ready. So you will have to include the right SQEs. Designing. This is so beautiful. First, you start with a visionary BOM structure. Like I showed, you identify the assemblies within that BOM structure and then the sub-assemblies, right? Like I said, cardiovascular system is one system within human body, but then the heart is an organ, and you can look at heart as a sub-assembly of the cardiovascular system. Why is the heart a sub-assembly? Because inside the heart there are various different parts that I don't know because I am not a doctor or a medical professional, but that's how I would best describe capital equipment design part, that you have to look at the visionary BOM structure, assembly, sub-assembly, components, part level, etc., etc., etc. There are so many details to it. Generally, for an optomechanical design, you start with optical models first. The optical engineers, they would generally provide you, this should be the focal length, this should be the aperture, etc., etc. And then you are supposed to, as a mechanical engineer, you're supposed to translate the optical specifications into realistic sizes and geometry. Tolerance studies for optomechanics, tolerance studies are very different than normal mechanical systems. And a lot of finite element analysis is also done at this stage to look at what kind of tolerances are needed and what kind of geometry, shapes, and lengths are needed. So during geometry optimization, you definitely do FEA. Manufacturability has to be of prime interest when you're looking in the design phase. You have to receive insights from your supplier, and you might have to even introduce new tools at the supplier. Oh my goodness, look at the optimization phase. In order to optimize the CAD models, you have to receive supplier feedback, testing, operations, and transportation feedback. You will have to probably do a design of experiment study or a design FMEA, and then finally you release the final bill of materials. Don't worry about design FMEA and design of experiments. I'll talk about that in other episodes. These are Six Sigma terms. You're also welcome to go and check it out. Some resources that are available online. Verifying. You have to verify at sub-assembly level, at the factory, and at the supplier side. After that, you have to integrate that sub-assembly into assembly and then at a machine level. And then you have to test it again, verify it again at factory, and then at the customer. Once everything is done, you have to add some control measures at the supplier and sometimes even at a second tier supplier so that your process is steady and strong and you receive your desired tolerances of your parts for years and years. Your control measures also need to be there at your factory and also should be provided as an operational guide to the end user and has to be available at the customer site along with the machine. You see, mechanical architecture is not a joke. It takes ages for people to reach this level of understanding. But yeah, it's a fascinating industry. Let's talk a little bit about translation of realistic sizes. When you receive optical models, you translate them to realistic sizes and geometry. Let's talk a little bit about that. in general, for TEM, for Transmission Electron Microscope, you have 4 or 5 primary disciplines. You have optomechanics, you have precision mechanics, you have some cross-disciplinary work, and then you have industrialization itself. So now I'm not talking about subsystems or systems. I'm talking about discipline, the type of skills that you need, the type of graduation certificates you need, let's call it that, right? So you need optomechanical knowledge for development of the electron source system, vacuum system, electron optic system, imaging detectors, energy filters, and FF fringe-free imaging components. What are these? We're going to talk about that in the upcoming slides. But you also need precision mechanics knowledge and skills to develop the autoloader system, the cryogenic system, the stage, mechanical drivers, electronics, etc. Cross-disciplinary because power supply and electrical components and software, mechanical cannot do it on its own. So you really need to get out of your bubble and be able to communicate and learn about other disciplines, constraints, and problems. It's interesting because as mechanical engineers ourselves, I don't think we ever think how difficult our lives are. We're just to get bullied and receive work from someone and just give our best and be disciplined and take the responsibility and solve the problems ahead of us because of our education system we're trained to be submissive, I would say. But look at what we are doing. Like when I made these slides, these are all my slides, by the way. I have made these slides. When I was making these slides for you guys, and when I'm speaking about it, I realize, oh my goodness, I deserve 6 figures and nothing less. I tell you, like monthly 6 figures, I would say. Not gonna happen, or maybe at one point, who knows. But what I'm saying is, as mechanical engineers, we need to be more proud of what we are doing. And if you are a startup, if you have the ambition of developing a capital equipment like a TEM system, transmission electron microscope system, or a hydrogen fueled automotive, or you want to build satellites, or you want to build a smart home, or you want to build data servers, you want to build complex machineries, and you want to actually build a startup around it, and you want to scale that startup, and you want to make your mark in the world, yes, this podcast is your best friend. Do contact me. We will join forces together and we will see how we could mutually benefit from each other. Enough of philosophy. Let's look here again, right? So a portion of the overall design work needs cross-disciplinary thinking, and everything that an expert does also has to be industrialized. So industrialization here refers to the type of design choices that would allow users to interact with the mechanical assembly with ease and would fulfill the reliability and quality requirements. For example, ergonomics is industrialization. The stage cannot be too below low, or it might need certain features to move the stage up and down. And that's what we were also talking about in the first episode when we were talking about the 6-axis stage. Please go and check out that video if you haven't yet. Looky here. Optomechanical engineering. What do we need? We have sensitivities, which are optical system sensitivities. You generally do that using the software called Zmax, and this is a whole discipline of studies. You generally go for a 4 years bachelor's and then 2 years of master's with 3 or 2 research theses out. So it's a whole thing here. Then from these optical system sensitivities, you go to mechanical system sensitivities, and then you have the ray analysis, you have vibration range analysis, temperature range analysis, etc., etc. Again, I could go on and on and on about it, but I need to keep it relatable to my startup founders, so I won't go too much into the details. Tolerances, optical elements, element selection and customization. So for example, you need, when I say optical elements, I mean your mirrors and your lenses. For photon optics, most of us, we have heard about lenses and mirrors to be made from glass. or ceramic at best, but for electron optics, you actually need metal or alloy mirrors or lenses. Sometimes you actually develop composite or ceramic optical elements like lenses and mirrors, and sometimes you use glass, but for electron optics it's mostly metal. You have to take into consideration the machining effects, the preparation effects, the post-processing effects. Now remember, when you have an optomechanical equipment, you will not have in-house skills and the equipment for the machining, preparation, and post-processing techniques. You are generally reliant on another supplier. So that is also where a supply quality engineer is of very good value, to have good communication between your supplier and yourself. And then, of course, the marketing team is a very good communication channel between the customer and yourself. See, everybody plays a role. Adjustment ranges, you should be able to adjust it in 6, actually 12 different degrees of freedom. We talked about it in the previous episode. Tolerance stack up. This is very common for different levels of the system or module. This is very commonly used mechanical engineering tool for almost, even if it's not a capital equipment, I think every mechanical engineer has been trained to work on tolerance stack up. Tolerance in general is to be very important, very simply put, if something is required to be 10 centimeter, it can never be 10. There are various different errors, operational errors, measurement errors, production errors that would come, because of which there will always be some error. So it will always be 10.1, 10.5, whatever it is. So you as an engineer, based on all the other requirements that you have to make the judgment. As an architect, you have to make the judgment on how much tolerance can your system accept. So if it's 10 centimeter, then can 10.01 okay, or should it be 10 point? If you want me to talk about tolerance, or if you want me to elaborate on any of these topics, write to me in my email that I showed you earlier. However, I'm more interested in being a fractional CTO for scale-ups and startups, so I am available for discussions on that. Let's come back to our podcast environment on optomechanical engineering. You have high power environments where you need specific coatings, specific materials, and of course you have to look at the lifetime of these materials and coatings, because high power, when I mean high power, I have worked with the UV light, etc., right? UV is extreme ultraviolet light, and the X-ray that I'm talking about in TEM and the electron optics for TEM, for Transmission Electron Microscope, for our product, high power, you really have to make sure that the mirrors and lenses are coated special custom developed coatings. Cryogenics, so going from a high power environment to cryogenics, you have to coat it, you have to choose the right material, and you have to look at the lifetime. And with lifetime comes calculation of lifetime is also another study. That's where reliability engineering comes in. If you want me to do an episode on reliability engineering, let me know. Vibrations are everywhere in a system like TEM. How to compensate those vibrations? You generally compensate it using mass. If there is a vibration in one side, you add mass on the other side to make sure that those vibrations are damped. Sometimes you also add active dampers and passive dampers. You can go on and on. Again, I can write books on this. Let's go to the next topic, which was the precision mechanics itself. Accuracy, precision, repeatability, reproducibility, and manufacturability. These are the 5 pillars of precision mechanics. There are amazing books written about precision mechanics, but most of the knowledge that's there for precision mechanics actually comes because of experience. How would you ensure accuracy? It's through a kinematic design, by looking at various different degrees of freedom, and we restrict the degrees of freedom in certain axes of rotation or translation. We could design flexures. We look at static stiffness, and in static stiffness, you have coefficient of thermal expansion, you have the thermal stability of the entire thing. And so the kinematic design, inclusion of flexures, coefficient of thermal expansion, and your thermal stability in general contributes towards the accuracy of the machine. And then when it comes to precision, you need a low friction and low hysteresis design. Your backlash has to be minimized and there should be no micro slip. And then your dynamic stiffness should be quite high so that all the vibrations are damped through active or passive damping. Dynamic stiffness to time varying input. Now that is very interesting. Time varying input. It could mean that at the beginning of the day, you start the machine, and because of that there would be some vibrations, and then it takes a while for the machine to stabilize, and that is where the dynamic stiffness to time varying input comes in. Your repeatability and your reproducibility. Repeatability depends on your environmental conditions, your design on low friction and hysteresis, and all other considerations we already talked about. What is the difference between repeatability and reproducibility? So in your machine, repeatability is the chances, the probability of receiving the same value again and again, non-destructively, if you measure one sample. So the chances of your eyes recognizing a potato as a potato for X number of times, that is repeatability. Reproducibility, on the other hand, is if you bring in 10 different eyes that are your family, your neighbors, and they each look at a potato, but then they are each saying, this is not a potato, this is a potato. So that is reproducibility. What happens when there are operator effect in the measurement output of your machine, and how the results change because of an operator effect, and also sometimes operating conditions. So that's why you need that's why the design of the machine has to be such that the repeatability and the reproducibility is extremely high, in the sense that human eye is incredible. If we see something at one position, unless there is a nervous system defect, if we see an image at a particular distance, it will continue to provide us with that image for an X number of times. Problem is, if you bring in various different human eyes, human minds, debates and questions come in. But that's a very loose description of repeatability and reproducibility. Repeatability basically means the amount of error a machine can provide or a machine can negate. And reproducibility is the amount of error that an operator plus the machine can include into a measurement. All right. So then the design has to have low sensitivity. You do that by isolating a metrology loop. Now, again, that goes into software. I'm not going to go too deep into that. You have to incorporate symmetry in your design, and you always need a minimum offset. Let's not go too into the details on that. A machine drift is also there, that your components have a lifetime, and as you use your machine, there's wear and tear, and therefore the machine drifts, the machine changes its geometry basically. Therefore, it could affect the reproducibility. Damping, like I mentioned, there are different time varying inputs. You could have various vibrations at various times of the day, and by positioning TMDs, tuned mass dampers, and RMDs, which is rotational mass dampers, in various different areas of the machine, you can damp those vibrations significantly. In general, having larger surfaces, they ensure damping. Indeed. Manufacturability, EDM, CNC, 3D printing, machining, post-processing. Wow. These are just jargons I wrote down here, but in reality, there are multiple manufacturing techniques for precision mechanics, especially for high-tech capital equipment. And yeah, it's all about knowing. In fact, the area of North Brabant and Germany and France in Europe are quite notorious for having small scale precision mechanics manufacturing facilities. In US, I don't think there are that many manufacturing facilities, but I think with the advent of semiconductor giants establishing their facilities there, I'm sure there will be a rise of precision mechanics manufacturing facilities. EDM, CNC are just examples. Like when I say precision mechanics manufacturing facility, I really mean developing really precise and intricate millimeter level flexures and components. Yeah, for that we need to be aware of GD&T rules on making the engineering drawings, tolerance, stack up, etc. And at the end, it's all about communication, communication, and communication, like I say. Wow, beautiful, beautiful. In general, this is a structured approach that ensures that every part of the TEM, from individual components to assemblies, are designed, tested, and refined to meet the standards. And this meticulous process it not only maximizes the TEM's performance, but also enhances its dominance in the market. The fourth piece of puzzle, your production control and operations control phase at system level. Look at the stakeholders. Marketing comes again. Marketing was here at the beginning. In the middle, they were gone. They were not needed. And then they're back again, along with system engineering, integration, PMOs, and suppliers. Here, you don't really need much of your designers. But let's go to the final product. Look at this beauty. The guys who are at home listening to the podcast, just to make you jealous, we're talking about this beautiful picture of a transmission electron microscope. On the top lies a cold field electron gun that is optimized for low energy spread, and it enables contrast at a higher resolution. Let's look at this. Let's look at the left. We have the electron source system, the vacuum system, the autoloader where the samples are retrieved and then transferred contamination free to another autoloader for investigation. At the bottom, you have the direct electron detector, and then you have the imaging filter. This is just amazing. This is just wonderful. The electron source system is the primary source of electrons, and it's crucial for the microscopy process. The vacuum system maintains a vacuum. Autoloader system is a mechanism for automatic loading and unloading of specimens, enhancing efficiency and contamination control. The electron optics system focuses and directs the electron beam to enhance imaging quality. The cryogenic stage system supports samples at extremely low temperatures, preserving their state for accurate imaging. The imaging detectors convert electrons that pass through or are scattered from the sample into a visual image. The supporting electronics manage and control the operations and data processing. Energy filter improves image quality. The stage and mechanical drives provide precise movement and positioning of the sample. Temperature and management system controls the temperature. The fringe-free components are very interesting. These are components that are everywhere around the TEM system, and then they are designed in such a way, or their materials are chosen in such a way that they reduce imaging errors by minimizing interference with the electromagnetic waves within the system. Amazing, right? It's just a bit of encapsulation and a bit of like selection of right materials there. Advanced monitoring and feedback system continuously monitors the system's performance for adjustments. And then you also have the structural components that are protecting the sensitive internal components of the microscope. Then you have the power supply, etc., etc. It's quite wonderful. Let's go back to the main page and go here. Whoa, the cold field emission gun, right? What does it even do? What are the components here? So you have a cathode emitter, and the cathode is typically made from a material like tungsten or zirconium oxide shaped into a sharp tip. This sharpness is crucial because it focuses the electric field to extremely high intensities at the tip. extractor. The component is positioned very close to the tip of the cathode. It serves to pull the electrons emitted from the cathode by applying a strong electric field. The electrons are accelerated to high energies by an electric field. There are electromagnetic lenses designed to focus the electron beam to a fine point, and they are critical for achieving high resolution in electron microscopy. The anode serves to collect the electrons after they have passed through the sample, completing the circuit. So let me go through the step-by-step process of electron formation in this electron source system. So under the influence of a strong electric field, the electrons escape from under the influence of a strong electric field generated by the proximity of the extractor to the cathode tip, the electrons escape from the cathode surface. This process is enhanced by the sharp tip of the cathode, which concentrates the electric field. Extraction. Once the electrons are emitted from the cathode surface, the extractor applies a potential difference. This electric field pulls the electrons away from the cathode and directs them towards the microscope sample. After the extraction, the electrons enter an acceleration stage where they are sped up by additional electric fields. This increases their kinetic energy to levels suitable for imaging. The accelerated electrons are then focused by magnetic or electrostatic lenses. These lenses control the beam's shape and size, refining the focus to a sharp point that is crucial for high-resolution imaging. The focused electron beam interacts with the sample, transferring the energy to the atoms in the sample. This interaction produces various signals, example, scattered electrons, which are detected to form an image. Finally, the electrons that have interacted with the samples are captured by detectors. The information these electrons carry is processed to create a detailed image of the sample at atomic or near atomic resolution. What a wonderful marvel of engineering. Let's go to the next system, which is the vacuum system. The process of vacuum formation, it begins with the initial evacuation of air from the cylindrical chambers using roughing pumps, such as rotary vane pumps. Like this stage removes the bulk of the air, bringing the pressure down to a level where finer vacuum pumps can operate effectively. Once the initial air is removed, the high vacuum pumps like turbomolecular pumps take over. These pumps handle lower pressures and are more effective at removing residual gases and achieving high vacuum levels necessary for TEM operations. For some applications, achieving an ultra-high vacuum is necessary. This is accomplished using ion pumps or cryopumps, which can remove even the smallest traces of gases from the system. Throughout the process, pressure sensors and gauges continuously monitor the pressure levels within each chamber. This data is crucial for ensuring that the vacuum conditions are within the required specifications for TEM imaging. Valves are adjusted and seals are checked regularly to prevent any leaks that could compromise the vacuum. Maintaining an effective seal is critical to the operations of TEMs, as any infiltration of air can disrupt the vacuum and the functioning of the microscope. Once the desired vacuum level is achieved and stabilized, the TEM is ready for operations. The vacuum conditions allow electron beams to travel without interference from air molecules, which is crucial for achieving high-resolution images. The vacuum system is a testament to the complex engineering required to support the sensitive and precise operations of TEM. For each component and step in this process, it is designed to ensure that the microscope can function at its best. Electrons are emitted from the electron gun and initially formed into a beam, and this is called a beam generation. The beam passes through the condenser lenses, which focus the electrons into a fine, coherent beam directed towards the sample. As the beam travels, the apertures refine the beam's width and intensity, blocking stray electrons to enhance image quality. The focused beam interacts with the sample, with electrons either transmitted through or scattered, depending on the sample's material properties. Objective lens focuses the transmitted or scattered electrons further, and they form an initial magnified image of the sample area being examined. Any astigmatism is corrected by stigmators and deflectors, and they are used to scan the beam across the sample in a raster pattern if in scanning mode. Projector lenses then magnify this image further, projecting it onto the detector system where it is captured and converted into a viewable image. Final image is captured by detectors such as CCD camera or other electronic detectors, and they translate the electron impacts into digital signals that can be processed onto images. How beautiful is that? The 6-axis cryogenic system. In the first episode, I showed a concept of that axis. So now that I'm talking about the real finished product, I'm just going to show you an AI developed image of an industrialized 6-axis cryogenic stage system for a transmission electron microscope. Samples are prepared using, this particular image. It features advanced components such as a cryogenic sample holder, dewar flask, thermal shielding, and a cold trap. The design highlights 6-axis movement capability, allowing for rotational and translational adjustments. This system integrates seamlessly with the TEM. It emphasizes flexibility, thermal stability, and precision engineering for accurate imaging. What does it actually do? So samples are prepared using cryofixation methods like plunge freezing, etc. They are rapidly cooled to cryogenic temperatures to prevent structural changes and to preserve in their native state. The prepared sample is mounted onto the cryo sample holder here, right here. Then the sample holder is inserted onto the cryogenic stage through a vacuum sealed entry port. The vacuum ensures that no external contaminants such as moisture enters the system. The system is actually kept cool using liquid nitrogen or helium. It's introduced into these liquid nitrogen or helium is introduced into the dewar flask, which cools the thermal shield and the sample holder. The cold trap captures any residual moisture in the vacuum to prevent ice formation on the sample. Temperature is stabilized. How is it stabilized? There are temperature sensors that monitor the cryo stage's conditions and controllers, and they adjust the cooling to maintain consistent cryogenic temperatures. The temperature shield ensures minimal heat transfer, preserving the sample's state throughout the imaging process. Positioning the sample. The 6-axis mechanism allows precise positioning of the sample in the X, Y, Z, and the rotational axis tilt, yaw, and roll orientations. Cryogenic imaging. The sample is exposed to the electron beams while its cryogenic temperature minimizes the beam-induced damage. The stage system ensures stability, preventing vibrations or thermal expansion that could distort the image. The electron beam interacts with the sample, and transmitted or scattered electrons are collected by the detector. High-resolution images are generated. Sample is removed after the imaging is finished, and the system prevents abrupt temperature change to avoid damage caused by thermal shock. And this particular thing about the system preventing abrupt temperature changes, this is a part of something called preventative maintenance. This is how you prevent wear and tear by just adding extra components into your system and keep it stable and maintain it. How does cryogenic temperature actually preserve the samples? Well, you have cryogenic cooling. It rapidly halts molecular motion. Therefore, it preserves the native structure of biological samples or materials. The low temperature also minimizes the effects of electron beam damage, such as breaking the molecular bond or introducing artifacts. And artifacts are nothing but errors in the images. The cold trap and stable cryogenic environment prevent ice crystals from forming on the sample, which could distort imaging results. Again, this is a preventative maintenance feature. This system is particularly valuable for applications such as cryo-electron microscopy. Let's go to our direct electron detector. Electrons pass through the sample and enter the imaging column. The energy filter removes scattered electrons outside the desired energy range. The direct electron detector captures high-resolution images of the transmitted electrons. Data is processed and stored for analysis using high-speed electronics. A second electron detectors could also optionally be added to provide a complementary data for diffraction or spectroscopic studies. The Falcon 4 DED, direct electron detector, is a state-of-the-art detector designed to capture electrons with high sensitivity, resolution, and speed. Now, here is a step-by-step explanation of how it works. Electrons transmitted through the sample in the TEM reach the detector. The detector directly senses the electrons, unlike traditional systems that convert electron signals into light using a scintillator. The Falcon 4 employs direct detection technology where incoming electrons interact directly with the active semiconductor layer in the detector. The active material typically is made of CMOS sensors, and it converts electron energy directly into an electrical signal. No intermediate conversion from electrons to light is needed, and that's an advantage. The pixel resolution that's made, the detector features a large pixel array, which is 8K by 8K resolution even. Each pixel independently detects electrons and records their energy and location. And this is a real product. I mean, Thermo Fisher's TEM system already uses it. I'm just talking about it. Noise suppression and dose fractionation. Falcon 4 is designed to withstand the intense electron beam without degradation, advanced electronic filters out the noise from thermal effects and stray electrons. The detector captures multiple frames per second, splitting the electron dose across different frames. Frame rate. Falcon 4 can achieve frame rates exceeding 1000 frames per second. This makes it suitable for both static high-resolution imaging and dynamic studies of processes at nanoscale. Intermediate storage. Frames are temporarily stored in high-speed memory before being processed. Falcon 4 incorporates onboard processing to compress data without losing quality. Images are processed in real time and integrated into TEM's control software for immediate visualization. So for Falcon 4, you have exceptional low dose imaging, you have high frame rates, you have high pixel density, and you have efficient algorithms that reduce storage requirements without sacrificing image quality. That's your state-of-the-art TEM right there. An energy filter. You need an energy filter because the purpose for this one is to improve image and data quality. And without proper data, your microscope isn't worth much. How does it work? As the electron beam passes through the sample, it interacts with the material's atoms. You have elastic scattering, where electrons that do not lose energy, they contribute to the zero loss signal, which is essential for imaging. And then you have electrons that lose energy because of inelastic scattering, and these electrons add noise, and that noise is used for analytical purposes. When the transmitted electrons enter the energy filter located in the post-sample imaging column, here you have the energy filter right here in the bottom corner. The energy filter uses magnetic or electrostatic prisms to disperse electrons based on their energy. Electrons with different energy levels are spatially separated into distinct paths. And then the energy selective slit is positioned at a point where electrons are dispersed. By adjusting the slit width and position, only electrons within the desired energy range, example, your zero loss electrons, are allowed to pass through. Inelastically scattered electrons are filtered out or selectively passed for a different type of analysis called EELS analysis. Recombining the beam. Now, so after filtering it, the remaining electrons are recombined into one single path, and then this beam proceeds towards the detector for imaging or further analysis. The filtered electron beam reaches the detector, like the Falcon 4 here, and then, of course, high-resolution images are created. What about the inelastic scattering? So if you have the if the energy lost because of inelastic electrons, they provide information about the material's composition, electronic structure, and bonding, and that is a different application, and that's for electron energy loss spectroscopy. Let's not go too much into the details on that. If you want me to do an episode on that, do write to me. Thank you. Finally, you have the fringe-free imaging components. What are these components? These are basically components in various different areas of the overall TEM machine. These are shields that are constructed from materials with high magnetic permeability, such as the mu metal. So these mu metal are specific metal that are made out of iron nickel alloy. They have high magnetic permeability, and they are generally used for TEM applications, but also other radiation-based applications. You have a CT machine. Then you have the stray field compensators, active compensator units that generate counteracting electromagnetic fields to neutralize any residual interference inside the column. You have your beam stabilizers, where you have the sensors and feedback loop monitor beam stability and correct for deviations in real time. And then you have grounded frames and isolations. Components of the TEM are electrically grounded to eliminate any static charge buildup. So these are fringe-free imaging. Step by step, the system's electromagnetic shields block external magnetic and electric fields, and it prevents them from penetrating the TEM column. The electron beam is passed through a series of apertures and lenses to align it along the central axis of the microscope. The stray field compensators measure and neutralize residual electromagnetic fields within the TEM. And then your sensors monitor the electron beam's trajectory for any disturbances. And of course, you have feedback systems to maintain a stable and precise beam path. But the advantages of fringe-free imaging is that it minimizes artifacts caused by electromagnetic interference. It stabilizes the beam and improves the microscope's ability to capture fine details. And it increases your reliability because you have better quality, good, reliable, repeatable images for research applications. That is how everything comes together in the grand scheme of things. The beauty of adding V-Model and Design for Six Sigma into the usual product development phase is increased communication between different levels of organization and a robust data-driven decision at every step. Before we conclude this episode, I want to go to the bottom right corner and talk a little bit about precision mechanics. So if you see meeting the specifications and performance, we talked about it earlier as well, it is dependent. So you have constraints like the vacuum, your radiation, resolution, accuracy, and precision. There are various different ways, various different dependencies on each of these constraints. So for radiation, for instance, you need the right material with the right permissibility level. Mu metals are there, but there are many other alloys and metals that are coming up in the market. By using the latest developed materials, the performance of the TEM could go further and further on. Vacuum-wise, you need a lot of different tests on the materials, but important thing is to look at the total organic content and the residual gas analysis tests of various components that go into the vacuum chamber of the TEM. For accuracy and precision, we have already done a good amount of talks on that. And then for resolution, you definitely need stable mounts and therefore a kinematic design, etc. Once again, let me know if you need me to elaborate on any of these topics further. For now, thank you so much for listening to me. Each topic would be discussed in details like this. I wish I could have time to give you more and more, because for each word, each technical jargon that I place in front of you, I can go on talking for an entire day. So that's why it's so hard for me to channel my thoughts and give you little by little. So thank you for bearing with me, and thank you for listening to me, and thank you so much for being there. Please watch the first episode of this topic, and I shall see you in the next episode of Transmission Electron Microscope.